So the last one here in this gas turbine is a Brayton-Rankine combined cycle. Okay. So already this combined cycle we discussed in the steam power plant. Okay. In the steam power plant, mainly our focus is on the bottoming and the topping cycle. So in the topping cycle we have taken the mercury, and in the bottoming cycle we have taken the steam there. Okay, but here we are combining the Brayton and Rankine cycle here. So there I have not discussed the Brayton cycle. Why? Because we have to see what is the Brayton cycle. That's why I postponed that topic to here. So here, what are the processes in the Brayton and Rankine cycle? You know, both the processes are same. What is that? Q addition and Q rejection both are at the constant pressure process, which is reversible, and work, turbine work and compressor work or the pump work both are at the isentropic process. Okay, that is what happened. So here in the combined cycle, what is happening? See here in this case, the Brayton cycle is working at a higher temperature. Why? Because the Brayton cycle is a gas turbine. Okay, always gas is at a higher temperature. Okay, and then the Rankine cycle is working at a lower temperature compared to the Brayton cycle here. Okay, so both are working in the processes that are followed in the both the cycles are same. Then what is the main difference? The main difference here is like in case of the Rankine cycle, the phase is changing from water to steam and then steam to the water. But whereas in case of the Brayton cycle, the phase, there is no phase change. No phase change. Okay, no phase change. Okay. And then what is the phase change and all? You go back and then study our thermodynamics. And next one is in case of the Brayton cycle, it is a compressive work and then turbine work. But whereas in case of the Rankine cycle, it is a pump work and then turbine work. Okay. So here, compared to the turbine work, the pump work is very less. Okay, very less. And now WC, the compressive work is not that much less. Okay, that is why here generally in the Rankine cycle we will neglect the pump work. Okay, so W net most of the time in case of Rankine cycle will become the WT. Okay, in case of the Rankine cycle, but whereas in case of the Brayton cycle, W net will become a WT minus WC. Okay, in case of the Brayton cycle, that is why the amount of W net that is produced, okay, W net that is produced in the Rankine cycle is always greater than the W net that is produced in the Brayton cycle for the same input of the Q, same amount of heat input. Okay, so here these are the advantages of the Rankine cycle over the Brayton cycle, but Brayton cycle is having other advantages. What is that? The Brayton cycle is very easy to install, and the components that we use in the Brayton cycle are very light. Okay, and then the starting of the Brayton cycle is very easy. Starting in the sense, I switched off the Brayton cycle based power plant, and if I want to start that, then if I switch on within half an hour, it will run at the full load condition. But whereas the Rankine cycle, if you want to make it run at full load condition, then it will take almost a half day. Okay, that we have already discussed. Then because of this main advantage, generally we couple this Brayton cycle with the Rankine cycle only to meet the peak load demand. Peak load means generally during the night times. Okay, during the morning times, and in case of the summer during the afternoon times, everyone will switch on the ACs, right? So to meet these peak load conditions, okay, we will switch on the Brayton cycle, and within half an hour it will be running at a full load condition, and it will complement the already running this Rankine cycle. Okay, that is what happening. So we have already discussed how the combined cycle will work. See, let's assume this is the first I will draw the Rankine cycle. Okay, this is the turbine, Okay, from the turbine, there is a condenser. Okay, from the condenser it will go to the pump here. Okay, from the pump it will go to boiler. Okay, so here instead of going to boiler, here it will go to the heat exchanger. So this will be the heat exchanger. So here in this heat exchanger, heat is given to this, and from where some other should lose its heat, then only it can give to the water here. Okay, so from where it is coming? Okay, this heat from where it is coming? See, after expanding through the turbine here, which turbine? This is the turbine, this is the gas turbine. So after the gas turbine, this exhaust gases are coming here. Okay, these are coming here, and then the heat whatever is losing from here, will be given to the water here. Okay, and after that again, this should be compressed. Okay, this should be compressed. So this is a compressor here. This is a compressor, and after that, again here there is a combustion chamber. Okay, combustion chamber. If you consider this as a closed cycle, this is how it is happening. This is a compressor. Okay, so here let's assume this is the 1, and this is the 2, this is the 3, and this is the 4. In the same way, I will assume this is the point A, B, C, and then D. So in the combustion chamber, Q1 amount of heat is given to this combustion chamber in the Brayton cycle. This is the Brayton. Okay, this is the Rankine. Okay, so here Q1 amount of heat is given in the combustion chamber, and after combustion, it will produce the WTB. B for Brayton, T for turbine. Okay, it will produce just that. After that, it will eject Q2 amount of heat here. Q2 amount is given to this. Okay, and after that again it will come and it will be compressed here. To compress this, we will give WC. I am not writing B. Why? Because the compressor is only in the Brayton cycle. We are not going to use any compressor in case of the Rankine cycle. Okay, and again it will go. The compressed air again will go to the combustion chamber, and the combustion again happen, and the cycle will repeat, so on. So here, where the water here at this position H2O water is pumped to this heat exchanger. In this heat exchanger, what happened? Heat exchanger, or like we can assume that it is a boiler which is having the inside heat exchanger. Okay, so whatever Q2 ejected from this will be given to this, so that the liquid will become the steam here, and that steam will be expanding in this turbine here. Okay, and after that it is coming to the condenser, and the steam will become the water here, saturated vapor water, and after that it will be again pumped to this. So here in this case it is producing WT Rankine, and here Q3 amount of heat is rejected to the atmosphere, and here WP amount of work is done to compress the saturated liquid to the here boiler or the heat exchanger. Okay, that is what happening here. So here what is the main thing that is happening? Instead of wasting this Q2, I am utilizing this Q2 to heat the water in the steam turbine. That is what I am doing. Okay, so if you represent this on the TS diagram, first let me draw this one. So here this is the Rankine cycle. One, two, 3, 4. This is the Rankine cycle. Okay, so how is the Brayton cycle on TS diagram? Okay, so this is the TS, right? TS. Okay, so the Brayton cycle in the actually this is the see the pressure is increasing like this. After that the expansion process is happening again. This is the Brayton cycle here. Okay, this is the A. Okay, so the burnt gases are entering the turbine here, and it is producing, and after that it is reaching the point B. Here Q2 amount is really given to this, and after that it is coming to the position C. That means heat rejection is happening at the constant pressure here, B to C, and after that C to D is the compressive process here, WC, and D to A is the heat addition. How much? Q1 heat addition. A to B is WTB. Okay, that is what happening. So from here Q2 is given to this. Whatever Q2 we are rejecting here, it is given to here, so that the water is rising from 4 to 1. Okay, in some of the cases, okay, we may think that whatever Q2 is given, it is utilized only for the evaporation. In that case it will be from here to here only. Okay, but whereas here in this case I have assumed that it is rising the water from 4 to 1. Okay, and after that here WT Rankine is produced, and after here in the condenser Q3 amount is rejected, and this is the WP here. Okay, so whenever you have the process like this, then the mu overall, what is the formula? Mu1 plus mu2 minus mu1 into mu2, where mu1 is for the Brayton and mu2 is Rankine. Okay, so we can directly write like this. So in case of the Brayton mu1, okay, what is the formula? It can be written as a W net divided by Q1. So W net is nothing but WTB minus WC divided by Q1 here. In the same way, the mu2, which is for the Rankine, equal to again W net divided by heat input. Here in this case heat input is Q2. Okay, then here it will become WT minus WP divided by Q2. Generally WP is very small, many times we will neglect this. Okay, this is how we can write. So sometimes instead of writing, if you don't remember this formula, then the overall efficiency equal to total work produced. Okay, total work produced divided by total heat input. Total heat input is only Q1. Where we are giving heat input only in the Brayton cycle. We are not providing heat input anywhere else. Okay, so here this can be written as see, always you need to remember here W net. Whenever I write W net, otherwise here I will write W net equal to, for the total T, equal to WTB minus WC into mg dot. Whenever I write mg dot like this, what is the unit of this? This is a kilojoule per kg. Okay, and this is the kg per second. So that what is happening here, this overall thing is going like, it is becoming the kilowatt. Okay, so kilowatt. Why? Because here, why I am writing here, I not worry to write like that. Why? Because here in this case what is happening, everything is mg, and here also mg is coming, and here also steam is coming, and ms dot is coming. But whereas here in this case it is a combination of two, that is why I am writing, plus WT Rankine into ms dot. What is the ms? Ms is a steam. Here I neglected the pump work, that is why I have written. Otherwise W minus WP also I need to write. Okay, if I am not neglecting. And here what is the unit of this? This is a kilojoule per kg, and this is a kg per second, so that the multiplication will become the kilowatt. And here what is the ms? S for steam, m dot is the per second. Okay. And when I write like this, then what's about the Q1? Q1 equal to, mg dot into calorific value of that fuel, whatever we burnt. Okay. And into combustion chamber efficiency. Okay. Combustion chamber efficiency. This is the Q1 here. This is how we need to write. See here, what is the main step? The main step is here, this is in terms of the mg and this is in terms of the ms. Okay, and this is in terms of the mg dot. So how much it will become? It will become the kilowatt here. Here also kilowatt, here also kilowatt. Then I can substitute these values in this formula, so that you can find out the overall efficiency. Okay, and apart from this, sometimes you may write like a mu overall equal to W net divided by Q1. Otherwise this can be written as, if I take the entire thing as one cycle, then W net will be nothing but the Q1 minus Q3, which heat input is given, where exactly heat is rejected only at the Q3. What's about Q2? Q2 is not rejected, but it is being utilized in the cycle. Okay, Q1 minus Q3 divided by Q1, this can be written as 1 minus Q3 divided by Q1. You can write like this also, this formula also. Okay, whenever I write like this, then in that case Q1 will be mg dot into calorific value of the gas that I used here, and whereas the Q3 equal to ms dot, okay, into, okay, whatever Q3, small q3 I will write, otherwise Q3, where here Q3 will be in the kilojoule per kg. Okay, then here it will become the kilowatt. Always we should be very much particular about the units that we substitute. Why? Because whenever the fluid is, whenever the Q1 and Q2 is not based on the same fluid, then the units should be very, very careful. Whenever the mass or Qg equal to, mg equal to ms, then in that case you don't need to worry about the units here. Okay, this is how we need to calculate. And here in some questions what happen, see here it is a completely came here. So instead of that, okay, it came only up to here. It came only up to here. Only up to here. Okay, it came up to only here A, B, C, D. I will say this as a E. Okay, and the remaining is rejected to the atmosphere. Okay, when the remaining is rejected to the atmosphere, then in that case what is happening? Let's assume here Q input is input is how much? Q1 amount is given. Okay, and what is the rejection? Rejection here, rejection is Q3 plus this much amount whichever is given to the atmosphere. Okay, which is the unknown value here. This is the unknown value, and here I am providing the in between intermediate Q2 I am providing, so that the the water is temperature rose from 4 to 1. Okay, so 4 to 1, that means there is a extra heat available, that extra is being wasted into the atmosphere. So here in this case, can I write mu overall equal to 1 minus Q3 divided by Q1? I cannot write. Why? Because here the rejected amount is not only the Q3, some other value here. some other value is unknown here, so I cannot write like this. Then in that case, how to find out the overall efficiency? Even in that case, I cannot write like this also. This formula also not valid. Okay. Why this formula also based, by the assumption that the entire heat rejected here is given to this, but here some of the heat is not given to this. Okay, so we cannot write this also. Then how to find out in that case? We can find out only by using this formula. So always this formula is straightforward and correct. Okay, so we can use this formula. Okay, and apart from this, sometimes what else they will give. Sometimes see, whatever heat rejected, this is not enough to rise this temperature from 4 to 1. In that case, there will be some extra heat given. Extra heat is given here by again doing the combustion here. So let's assume this is the point D, and up to point E it is gases are burnt, and then that heat is given to this. Okay, the extra heat is given to here, so that the temperature rising from 4 to 1 will be completed. So in that case, okay, in that case what will change? Here WTB is not changing, WTR is not changing, okay, and WC is not changing. That means W net of total is there any change? There is no change for this. Okay, there is no change. But what's about the Q1? Q1 is changing. How much Q1 is changing? See, mg dot into initially, what is the Q1 here? See, Q1 can be written as if I write in terms of the H, okay, then HA minus HD, okay, plus here also I burn some more gases, so mg dot, here you see here mg1 dot, here mg2 dot, some other fuel I burnt. Okay, how much fuel we will mention in the question. So here He minus HD, understood? This much heat is I given now, that also I need to add. Whatever heat input I have given, the entire heat input should be considered here. That is what I am saying. Then by calculating these two, again I will substitute this value here. Okay, by substituting the value here, I can find out the overall efficiency. Understood? Always the formula is the same. Only thing is, whenever they tweak the problem, how they tweak. Sometimes they say that they have given the extra heat so that the entire water will be converted into the steam at a superheated state, so and so, that is corresponding to the 1. In that case, what is the meaning of that? They have burned some extra gases so that some more extra Q is given here. Okay, that also will be added. Understood? Apart from that, sometimes what they say, when in the exhaust of the gas turbine, okay, the end state after the heat rejection to the steam turbine is so and so. They will mention that it is not equal to the C but some other place. In that case, what is the meaning of that? That means, it is not completing a cycle, but instead heat is given to the steam turbine, and after that, the exhaust is rejected to the atmosphere. In that case, I cannot utilize these formulas, but instead I can use this formula also, this formula only, by calculating the individual turbine work and compressor work and then the amount of heat input. Okay, that is how we need to do. We will see an example so that you will understand that.